I use the mic. Oh, okay. Okay. Yep. Okay, so there's a big echo, so let me mute this computer. Okay, so can you guys hear me? Yes, I think so. I see the subtitle in the Zoom. So let's get it started. Full screen this. So today I'm going to present SuGPT, AI-powered tool for smart contract decompile. And I'm Ethan Chen. I'm a second-year PhD student at CMU. And also I'm a researcher at Miston Lab and also a Sui ambassador. So a great thanks to the SuGPT team who helped to make this happen. And let's get it started. At the beginning, let me introduce the motivation of SuGPT. So I wonder if anyone here know the concept of Web3. So yeah, so Web3 compared to Web2 and let me move the talking apart. Wait, go ahead. Yes, okay. So compared to Web 1, that is only users as a reader, and Web 2.0, where user is a content creator. In Web 3, user is the owner of the assets, and they can transfer valuable stuff like money or tokens between each other. And this is what we call Web 3.0. And by the power of Web3, it used the decentralized blockchain to handle the data as a ledger. And users will have full control of the data and identity and digital assets by their private key. And this is blockchain-based. All the logic in this Web3 world is handled by the smart contract, which is the self-executing logic that is stored decentralized on a blockchain and can handle like if we shall transfer the money to someone or if I can get some money. And or like it can be used for gaming or for other purpose in Web3. So Web3 now is popular. As you can see, the token price is going up. Even the US President Donald Trump is launching his meme coin on the Web3. So and user is very engaging, and there's a lot of cool application and lots of opportunity. But also Web3 user have more power, also come with great responsibility. Web3 is dangerous. So blockchain technology is new and is decentralized, very hard to trace. So at 2023, there's a report for 1.3 billion of dollar is hacked by the blockchain smart contract. And there's a lot of phishing attack or malicious application to scam people's money. And we see this every day in the blockchain world. And that is why we build this decompiler. So here are some examples, like some people try to scam using Elon Musk Twitter or just fake image for Twitter for free giveaway. And once you interact with that smart contract, you will just give your money away, and then you figure out it is a scam. So in Web3, it is zero trust and always proof. But users like you and me, you may don't know where to prove it yourself. That is why we build a SuGPT decompiler. So SuGPT decompiler is a tool to let users to understand the logic of a smart contract. So right now we already have decompiler at blockchain. Like it can decompile to something like this, which is still very hard to read. And even though there are some machine-based decompiler can decompile back to machine bytecode, you can just see the variable name is V0, V1, and it is poorly syntax. So without domain knowledge, you cannot understand how this smart contract do. So it is like according to connected load theory, we need to remember these variable names, and this variable name is just VD or V1. Is take a lot of effort to understand this code. And meanwhile, there's a lot of research is working on how AI-powered decompiler can create a human-readable code, but none of them is applied to Web3 smart contract. So our research aims to fill this gap. We build a AI large language model-based decompiler with GPT-4, and then we use GPT-4o. And basically we use prompt engineering from using in-context learning and fusion learning to empower the AI to decompile the smart contract based on the decompiled bytecode. We use it, turn it, and we map it back to the source code. So basically we teach AI how to rewrite the bytecode back to the source code. And originally I want to have a demo, but because this is not my computer, so I will skip this part. But basically we use this decompiler to put at a developer hackathon, and we decompile the developer's contract in live, and they are very amazed for how our decompiler perform. And based on the decompiler work we've done, we have 4 research questions. First research question, can CGPT approach accurately to decompile most smart contract bytecode into the most logically equivalent most smart contract? And the second question is, did decompile result have high readability? And the third question is, can the result be recompiled or executed successfully? The last question is like, now we have the tool, how to use it? How stable is the use for large language model powered decompiler? And does it tend to generate hallucination? And how users is intend to treat this decompiler? Okay, so for the first question, for how stable the large language model powered decompiler is, we use the top 30 package at the Sui blockchain. Basically, we decompile the smart contract bytecode, and we try to recompile it again. And we find a 73% recompilation rate for GPT-4o. And for the older version of GPT, which is GPT-4 Turbo, we find it is 55%. So, but the 55% is very amazing because at this version, the AI don't have any domain knowledge for this smart contract. So basically, the smart contract for Sui is launching like at 2023 May, and GPT-4o is the knowledge cutoff is 2023 April. So basically, without any prior knowledge of a smart contract language, AI can decompile it and make it to 55%. So which is, we can apply this to other domain-specific language if we want to make it more easy to read. And if AI have more knowledge, like the later version of GPT, it can do it even better, which indicate like fine-tuning with some data can even enhance this performance. And another question is, how can we decompile, and is this the logic equivalent, and how stable it is? So we use the example code from Sui official repository, and we decompiled it and compiled it and run the unit test. And we find that 6 out of 10, there's a typo. So 6 out of 10 can pass the unit test. And the rest of the 4 can pass after fixing some hallucination. So we find that AI still sometimes hallucinate a function code name, but basically the logic is correct. It is readable. Just have some occasional hallucination. And finally, we proceed to do user study with real developers around the world. And we have 2 groups of participants. The first group of participants, we have 90 minutes of user study, and we do an interview with them. And the second group, and they need to do a bug caching task. Another group of participants, they basically we use AI to decompile their own smart contract and interview them. And we find that most of the users guess the decompiled code is actually the source code, even though it is not the source code. And we use the NASA test load index to understand how users perceive the decompiled code and compare to the source code and compare to machine-based decompiler. And we find that for all dimension for NASA test load index, the decompiler, AI-based decompiler will have similar connecting load than the source code and significant lower connecting load than the AI, than the machine-based decompiler. And yeah, since I'm almost out of time, I'm gonna skip some detail, but for the interview insight, you can find it in your paper. And one very interesting thing is AI actually can rewrite a code that after decompile the code is actually better. The variable name is choice is better than the source code. So the source code is using the variable name is in leaderboard and AI just decompile to exist. And participant actually think this is better than just the source code. So this tool has the potential to do even better than source code, which make me a bit sad because I write the source code and participant didn't like it. Yep. And another thing is using the AI powered decompiler because it is more easy to read. So users, well, not likely to give up. So because of that, they are more likely to proceed with audit and actually check if the smart contract have vulnerability. Compared to using machine-based decompiler, they may just give up because it is too hard to read. Okay, and that's it. And there are some use case that we can use CGPT to audit to save developers time because it can educate developer. And in the end of the paper, we also discussed the concern for the CGPT that some people may think if someone just decompile and steal your intelligence, and basically some participants indicate there's no need to worry because in the smart contract, it is already open sourced. And also like, what if someone decompile and hack you? And this is also don't need to worry that much because if even though there's no AI-based decompiler, a smart hacker can still understand by reading a byte-based source code. Yep, and that's it. That is the end of my presentation.
So thanks, Ethan, for the great talk. Any questions?
Yeah, thanks for the talk. And I have a question about the decompilation is that I'm not familiar with the smart contracts, but in the traditional compilations of some binaries, there is some information loss, for example, for the length of the array and some specific types of the variables, such as you cannot just directly identify a variable of an integer if it is signed or unsigned. So when you analyze some problems about some security problems about that, you cannot identify from a decompilation to identify whether this binary has a buffer overflow or integer overflow. So is the decompilation of the small contracts has similar problems, and if so, does that matters? Yeah.
Good question. So actually the decompiler of the smart contract also have, so for the smart contract, it also have integer overflow or some security concern like the sign of unsigned, but we use the smart contract language is the move language. So basically language syntax itself is effectively address this problem. So all the variable in move is unsigned. So we don't need to worry about the sign. And also like if there's an overflow or the type mismatch, it will just cause error. And for AI, but there's indeed a lot of information is lost, like developer add some comment or developer will use some markers or some scripts to help the smart contract component. All this component information was lost at the decompilation stage, which will make the smart contract more redundant. But this doesn't influence the purpose for CGPT, which is help people to more easily audit a smart contract and understand how they work.
Oh, we have time for one quick question.
I don't know if it's a quick question. Because I see you mentioned the hallucination for the ChatGPT, for the GPT model, for the larger model. So I want to know that if such things happens during your generation code part, or how do you figure out those things?
Oh, you mean hallucination?
Yeah. How do you like guarantee that your final output will be the correct one?
That's very hard, actually. We try very hard, but like at best we can get is 73%. So, but like other paper we see in the C programming language is also around 80%. So there's a gap. There's still some research work to do for how can we make AI not hallucinate. And the best thing we can do is right now we are trying to make AI to iterate. So basically, it decompile, it run, and you put the error back to the AI and try to iterate and make it actually can run. Yeah.
Thank you.
So let's thank the speaker.
Yep. Thank you.
Now next talk is before and after the effect of EU's 2022 Code of Practice on disinformation.
Where are the slides?
Which PDF is yours?
Okay, great. So, hi everyone. My name is Papadogiannakis Emmanuel, and today I will be presenting our recent study called Before and After the Effect of EU's 2022 Code of Practice on Disinformation. Now, a quick outline. I will describe the motivation behind our work. I will then shortly talk about how we did our study, our methodology, and finally present you our findings. I'm certain that most of you have heard about fake news and online disinformation. But the thing is that when people think about fake news, they usually think that it's just about politics, right? However, disinformation, online disinformation, is also a very profitable business model. Websites that spread misleading or even false content can generate billions of dollars each year. In this work, we focus exactly on these websites, misinformation websites that generate advertising revenue through online ads. So, to address online disinformation, the European Union introduced the updated Code of Practice on Disinformation in June 2022. And this Code of Practice basically asks from ad tech companies to stop funding websites that publish misinformation, that publish fake news. And the idea behind that is that if people don't generate money out of fake news, then they will probably stop spreading fake news. And I should note that this is a self-regulatory standard, meaning that ad platforms have to be willing to do so. But the European Union is trying to turn it into a proper regulation and integrate it into the DSA. Now, here I have a high-level overview of the advertising ecosystem and how money flows from advertisers through ad networks and eventually to disinformation websites. The goal of the Code of Practice on Disinformation was to stop disinformation websites from generating money, from making ad revenue. So to basically cut the financial incentives of disinformation spreaders. The key question here is, has anything actually changed since the Code of Practice was introduced? Do ad networks continue to work with fake news websites? Do they place ads on such websites? Now, to answer these questions, we need to focus on fake news websites, right? Disinformation content. And to discover such websites, we use some other published papers as well as Media Bias Fact Check, which is a very credible fact-checking organization. And we formed a list of almost 2,500 misinformation websites. And our list is free to use, and you can access it either through the URL or the QR code. So we now have a list of misinformation websites. We know which websites publish false content. How do we know which ad networks work with these websites? Who places ads on these websites? And to answer this question, we studied an ad fraud prevention standard called ads.txt files. And these are simple text files that website publishers use to basically list the companies, the ad networks that place ads on their website. So if you look at the example here, you can see that BBC, for example, is working with Google and allows Google to place ads on its website, right? That's pretty straightforward. The problem is that these files that I talked about, these ads.txt files, are actually published by the website owners. These are the same people that publish fake news, so they could also publish fake files. So for this reason, we also studied a different standard called sellers.json. And these are also text files, but they are published by the ad networks this time, so the other side. And they basically list all the websites where they place ads. So again, here this time we have the same example. We can see that Google acknowledges that BBC has an advertising account with Google and gets Google Ads. Next, we analyze those files and discover the business relationships among misinformation websites and advertising networks. So when a website says that it gets ads from an ad network and the ad network also confirms that it places ads on a website, then we have a business relationship, basically a business contract between two entities. And we focus on these websites, on these relationships, the intersection of what both sides agree on. So enough of background. Let's now see what impact the code of practice on disinformation had. What we did is that we collected and studied the business relationships before and after the code of practice was signed. And at first glance, as you can see, we found that there are some advertising networks that have stopped working with a lot of misinformation websites after signing the code of practice. So this means that they stopped placing ads on such websites and stopped giving them money, stopped funding them. So one would say that this is great news and it was successful, but then again, why am I here today? Unfortunately, things are not so good. We took a closer look and found that while some misinformation websites were indeed demonetized, they were low traffic websites. They were websites with hardly any visitors. And the big misinformation players, those that spread a lot of fake news and reach thousands or even millions of people, continue to generate a substantial amount of ad revenue. I have a very short example here focusing on the misinformation websites that Google is working with, basically placing Google ads on. And the bars represent the websites that Google demonetized after signing the code of practice. So they say that they want to stop fake news, and this is what they did. You can see that they mainly defined it the less popular misinformation websites. And the most popular ones continue to generate ad revenue and work with Google. So popular misinformation websites still get ads and make a lot of money. Now, one could argue that these websites perform some form of ad fraud or even deceive ad networks and they hide between other websites. This is not true. We found that even the most popular disinformation websites are explicitly stated as partners of big ad networks. For example, you can see that Google explicitly states a business contract with Breitbart or even Sputnik and other popular or let's say infamous disinformation spreaders. Now, if you are interested how fake news websites can abuse the advertising ecosystem and make money out of it, you are welcome to join my presentation tomorrow on advertising fraud. Finally, we did a comparison between reliable and unreliable news websites. So basically, real news versus fake news, and found that ad networks do not really differentiate between unreliable and reliable news sources, and they work with almost as many of both categories. So they don't really care about the truth of news sources. They just want to make money. And this analysis was focused on ad networks that have signed the code of practice, like Google and Microsoft. And now the final part is that some ad networks could argue that, you know what, we used to have a business contract with these disinformation websites, but this is not the case anymore, or that we don't place ads on these websites and other things. So what we did is we studied exactly this idea. We visited misinformation websites from various points around the world and collected the ads that they display. When we studied the ad networks that place those ads, unfortunately, we found that even ad networks that have signed the code of practice on disinformation continue to place ads on misinformation websites, and therefore giving them money, giving them a reason to spread more false content and a way to survive on the web. And to make matters worse, the ads that we discover come from very respectable and reputable brands. And we even found some Fortune 500 companies advertising on big disinformation websites. Finally, at the bottom here, you can see that we found some ads from misinformation websites in other misinformation websites. So this means that you visit a fake news website and you get an ad to visit a different fake news website. So not only do ad networks fund misinformation content, they also promote it. So to recap, in this work, we studied the strengthened code of practice on disinformation that attempts to demonetize disinformation websites on the web. We found that its impact has been at best modest. Ad networks have indeed stopped working with misinformation websites, but only with the unpopular ones. And the big disinformation spreaders continue to generate ad revenue and survive on the web. And this ad revenue often comes from very respectable and big brands, basically advertisers. So altogether, this is the bottom line. The code of practice is a step in the right direction, but there is still a lot of work to be done. And hopefully now that the EU is trying to turn it into a proper regulation, things will improve. So the one thing that I would like for you to remember from this presentation is that the code of practice did not make a significant impact on demonetizing disinformation on the web, and there is still a lot of work to be done. Thank you very much for your time, and I'd be happy to answer your questions.
Thank you for the talk. When you say that the websites were demonetized, are they still online or were they taken offline? And if the latter is the case, would it be a similar churn rate to just random websites? So
That's a very good question. Most of the times they are not taken down. We've done a previous study and show that disinformation websites also have other ways to survive instead of online ads. They usually have their own stores, or online stores, I mean, or they sell some seminars or books and stuff, or get private funding because there are some politicians that want to push specific agendas. So sometimes they find other ways to survive, but demonetizing them does not necessarily mean that they are taken down. But it's a proper way to ensure that people don't just spread false information just to make money out of it.
Thanks a lot for this interesting talk. If you were to become the next commissioner in charge of regulating the data sphere, what do you think would be a more impactful and better approach to regulate this to achieve the goal that was originally intended to be achieved?
Yeah, that's an interesting question. It would be a tough position to be in, but I guess turning this code of practice into a regulation will have a significant impact. At the moment, the code of practice is just self-regulatory, meaning that ad networks might want to contribute towards this direction or might want to do it to get a better name. They are not actually forced. If they are forced and there is proper regulation that has an impact on their business model, then I guess they will comply with it. And if there are huge fines like we saw with GDPR, then they are most likely to follow the rules.
So let's. I think there are still some people who are interested in questions, but we're out of time. So maybe you can advertise your poster, and then maybe people can come.
Yeah. The poster will be today. I think it's 5:15. So if you have more questions or if you are interested in such topics, I would be happy to discuss them with you. And yeah, thank you very much.
So now next talk will be responsible diffusion models via constraining text embeddings within the safe regions.
Okay, good afternoon, everyone. We are the team from East China Normal University. We are very happy to have the opportunity to share our work with you today. Our paper title is the Responsible Diffusion Model while Constraining Text Embeddings with Safe Regions. Okay, let me first introduce the background of our work. In recent years, with the rapid development of diffusion models, the large-scale text image model have demonstrated impressive capabilities. Users can now generate diverse and highly realistic images using simple text and prompts. And many online platforms now offer state-of-the-art text-to-image models, attracting a large number of creators to generate images every day. However, these text-to-image models also pose significant security risks. They are typically trained on large-scale data sets scraped from the internet. Although the base data filtering is applied, these data sets often still contain unsafe content and hidden social bias. The models may inherit and amplify these risks. For example, the models can easily generate sexual or violence content. Even though with the safe input prompt, such as a beautiful woman, the models might still produce the nudity images, and the models is hip to clear social bias for its insistence. The daughter image often generate the white male daughters. Some method has been proposed to address this issue, but there is still some distance to achieving the responsible generation. For example, the word filtering for input can only detect explicitly unsafe words, while the consent erasure method only works for specific concerned words and often produces sufficient results for the other words. Therefore, we attempt to address this issue from a different perspective. Our goal is to manipulate input text embedding in the latent space, steering the textual condition toward safer regions to prevent the generation of inappropriate content. We can observe the that features in embedding space typically exhibit linear properties. Intuitively, this means that moving a sample along a certain direction in the feature space can get a sample with different attributes but the same label. Therefore, we can identify a safe direction to constrain test embedding with a safe region. So, as so in the figure, switching towards the safe direction does not affect image of apples because the apple representation has not the other manifestation along the safe dimension in the feature space. Meanwhile, for the neuter image, the safe guidance simply adds clothing without altering the main subject information. A straightforward approach will be to directly add or remove sentence words in the text, but this often fails to achieve the best results while compromising the original image quality. A key reason is the inherent discrepancy between the text and image domain in generative models. Therefore, we leverage the diffusion model's own knowledge and optimization methods to identify a direction that can guide self-generation in the image domain. In short, we employ a related strategy similar to moving away from or towards certain concepts to find the direction. First, we consider an implicit classifier. The CO is the target concept that we want to close or away from. According to class-free guidance, the gradient of this classifier can be written as this form. So we can get a noise estimates that are far away from or close to the target concept. Then we can minimize the distance between this noise and the noise that at the direction vector. We can find direction vector that steer the image toward or away from the target concept. This is the overall framework. We exploit the diffusion model's inherent knowledge to identify precise semantic direction in embedding space. We optimize this direction intuitively across all type stacks during the denoising process. This choice is motivated by the fact that the test condition is applied at every diffusion state during the image generation. Generally, we can initialize the direction vector with the same shade as the prompt embedding. However, we find that this approach often results in destroy and wipe image. To obtain more precise semantic direction and X-ray convergence, we propose to represent the semantic direction vector using low-rank matrix. We can learn a safe direction by moving away from the defining unsafe concept. It should be pointed out that our unsafe concept, including violence concept, such as the violent, sexual, disturbing, and so on. The reason for adopting this strategy is that it is difficult to list all the upside of the unsafe concept, such as the upside of the nudity is just wearing clothes and the others. From the quality results, it can be seen that our method generates safe image while preserving the original semantic content without introducing the significant alteration to the source imagery. In quality experiments, we also achieve the total results compared to the other methods. And we can reduce the generation of multiple unsafe categories of content at the same time. In addition, our method can maintain good performance in the face of malicious prompts carefully designed to generate harmful images. We also can learn direction vector related to the sensitive attribute to achieve file generation, such as the gender and race. We also use the more challenging prompt template in our experiments, such as a portrait of a successful profession, because the successful in diffusion model often generate the male and white people images. Our method can mitigate the potential gender and race bias about the profession in the diffusion models. We also quantitatively validate the impact of our method on image fidelity and text alignment. The results show that our approach maintains the high image quality and text image alignment, demonstrating that the semantic direction we learn is accurate. This also ensures that our method can create usability that can be used on the online network image generation platform that require the high image quality. Our method also demonstrates strong transferability, as it only involves manipulating the point embeddings, and it is independent of the model space architecture. This approach can be easily applied to various diffusion models, including the Stable Diffusion XL, Stable Diffusion 3, and the lattice flash models. Moreover, our method is orthogonal to a system fine-tune approach, so our method can be used together with them to build a more responsible diffusion. When an online platform wants to deploy an image generation models, our method can be acted as a middle line of the defense in their pipeline to ensure that API service or online service they provide are security and controllable. Okay, thanks for listening. This is our presentation today. More details can be found our paper. Okay.
Okay, thank you for your presentation. As you mentioned, your method can be applied to different diffusion model. So to my knowledge, there are some diffusion models that have more than one text encoder, such as SD-Child and, such as SDXL and SD3. How do you work with multiple text encoders at this point?
Okay, thank you. Thank you, question. Yes, as you mentioned, there are some diffusion model have multiple text encoders, but as far as I know, the current diffusion model, regardless how many text encoder they use in the text encoder stage, but they will be contain a single embedding before they fed into the subsequent diffusion model to generate images. So we focus on the final single embedding because it contains the implication the information. Okay.
Any other questions? If not, I have a question. So how do you ensure, if you think about the definition of safety, it is different for different countries, different locales, etc. So how do you generate a directional embedding that works across different locales, especially when the definition of safety can be quite subtly different across locales?
The safety is defined in our work. We are following the private words. We will predefine some unsafe concept, like the violence sexual distributing of blood, and the other was about some appropriate content. These are general concept concern. The space and the space concern different in the country. I think it's the same method. We can defend the different concern in really scenarios.
If there are no other questions, let's take the speaker. Now next talk is semantics-aware cookie purpose compliance.
Hello everyone, I'm Betsy Chen, a PhD student from the University of Queensland. I'm glad to be here presenting our project, Semantics-Aware Cookie Purpose Compliance. The website cookies are widely used today. A website may use cookies to store users' login status and to remember and also track the users' activities for the statistics purpose or the marketing purpose. And such information including the user's login details, all the personal preferences, and the customized settings. And cookies now has served as a fundamental component of the website functionalities for many years. However, actually, most website cookies raise the privacy concerns. Like the example showing the picture, the NID cookie is used to show the Google advertisements in Google services for the seeked out users. And Facebook also sets the specific cookies to track users' activities, even though they are not logged into the Facebook. And X also sets the personalized ID to track users' behaviors, even though they don't have the X account. Therefore, to regulate the web cookie usage behaviors of the web providers, some countries improved their data protection regulations to regulate the web providers for the user's privacy. Like the very popular regulation for GDPR, Australia Privacy Principles, CCP, and also the new one, DPDPA. The websites need to respond to such regulations in their cookie declarations, either using the cookie policies or the cookie consents. Otherwise, they may lead to a huge penalty. And also the GDPR also defines 4 types of the cookies. The first one is necessary cookie and preference cookie, statistics cookies, also the marketing cookies. The necessary cookie is actually linking to the core function to the website, like the user's login, also some payment information linking to the shop marketing website. And then, okay. I think it missed one. Okay, I can introduce myself. I think it's missed one slide. The preference cookie is to save users' preferences, like some language setting. But it's not the core function of the website, but just save your some privacy settings for your experience. And the statistics cookies actually is to track users' behaviors, like for the websites to analyze your habits or analyze your interests. And the marketing cookies is for the personalized advertisements. And then this is an example to the cookie policy, like the cookie usage part for the cookie name in the table, and also the cookie purpose. The functional purpose refers to the defined reference purpose, and also the domain of the cookies. Such very important part need to be displayed clearly. Besides the privacy policies, most websites prefer to use cookie consent to display the cookie usage for the users. The cookie consent also can get the users' permissions for their cookie collection behaviors. Users can choose to reject one of the one of the cookies purpose and then save their preferences. Nowadays, nowadays most websites use the consent management providers, as we call CMPs here, to automatically generate and also display the cookie consent and also the cookie banners for the users. The example shown here is also the well-known CMPs called the cookie yes. However, actually, the previous studies has found that most website doesn't satisfy the data protection regulations, even for those using CMPs. And the website providers still can modify their cookie consent, even though this automatically generate, and they still can have the permission to modify it, and then just display the modified cookie consent by themselves. So we propose Cool here to identify the cookie usage in the website. The Cool use cookie values to analyze which the purpose they belong to. Compared with the previous study, some study use the meta-information based, like using the machine learning algorithm to use lot of the attributes of a cookie to train a model. And we only consider the most important part of the cookie, including the values, like what information they store here. So that we call the semantics-aware for the cookies. We extract the segments appeared in the cookie values. You can think the segments for the cookie values like a word for a sentence. And a sentence has many words to present its meaning, so as cookie values. Like the cools will explore those potential segments, like the words in the cookie values, to help us analyze what such kind of the cookies are belongs to which purpose. The challenges are that it's difficult to summarize the format or the patterns of the cookie values. The web providers tend to define the patterns for their cookies by themselves. Even for the similar cookie from one website, their format or common patterns are not the same. Like the example shown here, the statistic cookies from Google Analytics, starting with JA and JS. And also, some cookie values are encoded, hashed, or even encrypted for the security reason. And such value is it's like the unreadable for the humans. And also the cookies with identical values or patterns may serve distinct purpose across the website. Like the example shown here, if the session ID may a random ID for like a random number for ID, but if it stores with the timestamp, it may serve as a statistics cookies. But if it stores without other tags, it may serve as a necessary cookie. So to solve those challenges, we propose Cool here. The Cool uses the automatic approach to first extract the segments in the cookie values using the phase one. So this the phase one aims to figure out the first two challenges. And then the Cool fine-tunes the value inferred classifier using the large language model. This phase aims to solve the last challenges. And finally, the Cool will mix the potential compliance checking in phase three. The phase one has 5 steps. The first one, based on our observation, we first summarize the segments into 4 categories. It's plain text, frequent occurrences, recognizable patterns, and also the web conventions. The first step, we call it the value decoding to get the original text for the cookie values using some common hashing method or encoding methods. And here is an example for our value decoding step, like how can we get the original text. And then the step 2 is to extract the fixed patterns, like the timestamp here for the recognizable patterns. After that, the Cool will get the plain text segments in step 3. As in step 3, we will use the ARTK technique. The step 4 is to identify whether the context is random or not, and we will filter out those non-useful things. The step 5 will use a customized learning algorithm to get the prefix and also the suffix for the cookie value segments. Like the web conventions here for the JA and JS, like the previous picture showed, and also the frequent occurrences. After extracting all the segments, we fine-tune the GPT model. The input will be the cookie's name and also the segments we detected in the cookie values, and then the domain of the cookies. The output will be the value inferred purpose. We also evaluate our classifier with the state of the art, and the performance of the cookies is better than them. Achieve a F1 score with 0.95. After getting the segments corpus in phase 1 and also the fine-tuned model in phase 2, the core makes the potential compliance checking. It will compare the value inferred purpose and also the declared cookie purpose. The core will use the cookie values to first get the value inferred purpose, also use the previous fine-tuned classifier. And the declared cookie purpose are extracted from the website provided cookie declarations, either they are using the cookie policies or cookie consents. And then we define 4 types of the issues. The first one is no cookie usage declaration, like the website didn't provide any part of such things like the cookie policy or cookie consent. And then it's the implicit cookie consent. Like some websites pursue the user's consent to their collection behaviors by default. Like they only provide cookie policy and they didn't ask the permission in the cookie banners, or like just when you first log into the website or you click in the website, even if they have the cookie consent, but they didn't display such kind of things for you. And then is the unclaimed cookie usage, like some cookies detected by the cores, but they're not declared by the websites. And then is the potential cookie purpose violation, like the value inferred purpose is not matched with the cookie declared cookie purpose. After Core applies among top 1,000 websites, we found that most websites have the cookie usage issues. And among the detected cookies, actually only a few of them are the value inferred necessary purpose. Yeah, that's all of my presentation. And we propose Core to make the value inferred analysis of the cookies. And also we construct a segments corpus. Thank you. Thank you.
Thanks for the talk. In the beginning, you mentioned that there are different regulations in different countries, and I wanted to ask you how you collected the data. Do you collect it from different countries?
Yeah, we collect through the Alexa top 3,000 website for the cookie values.
Yes, but do you collect, when you collected the cookies, do you visit the website from different locations?
We didn't visit it from different locations. Like we actually set several test accounts, but only in the same location. Like the IP address may be the same. Yeah.
Thank you.
Any other questions? If there are no other questions, maybe I have one more question. So if you think about the policymakers' intent, they are actually intended to track privacy violations other than cookies. For instance, local storage or fingerprinting could also be potential other ways to track users. So have you thought about how to extend the work to extend those other elements?
Actually, such kind of the questions also appeared in the rebuttal phase. Yeah, like I think if such kind of the approach can work in the cookies, it may also can work with other domains or the like the fingerprint part or other local storage part. So it may can explore more domains using this approach. But in this project we only focus on the cookies.
Thank you. If there are no other questions, let's thank the speaker.
I don't know.
Thank you for the presentation.
Okay.
I'm wondering if you use your approach, you compare the cookies that you obtain with your approach with existing heuristics. For example, I'm thinking about tracking cookies.
if you compare, for example, existing heuristics with training cookies that you obtain with your approach.
Sorry, I didn't get your point. So could you just repeat your question?
So what you do is, from what I understand, is to extract some cookie segments, and you identify their purpose, right?
Yeah.
Okay. So I think that one of the most prominent use cases is web tracking. So like web tracking cookies, do you consider this case?
I guess what kind of you mean? You mean besides the values, domains, and names, other attributes?
Sorry.
So what's your point?
Okay. I think there is. It's fine.
Maybe you can ask
Thanks.
me later.
Maybe I will ask later. Thanks for the presentation anyway.
Okay.
So now last talk will be logical and causal fact checking with LLM-based multi-agents.
Hello everyone, I'm Lin Hu, an associate professor from Beijing Institute of Technology. Today, I'm very happy to share our work titled Logical and Causal Fact-Checking with LLM-Based Multi-Agents. This is a joint work with my students Ma Jiatong, Li Rang, and Fu Wenbo. First, I introduce our background and motivation. In the digital age, people are exposed to a vast amount of unverified information. One of the major challenges we face is that everyone can be an information publisher, and the social media rapidly disseminates the information, no matter is true or false. This creates a pressing need for fact-checking. Fact-checking helps enhance the credibility of information, and it can reduce the spread of misinformation and improve the public trust in media. Fact-checking often requires deep logical and causal reasoning and understanding. This diagram shows the standard pipeline. We usually decompose a claim into simpler subtasks and then retrieve necessary evidence and then conduct subtask reasoning. Finally, we integrate the subtask results to reach the final answer. In this pipeline, we should ensure that the decomposed subtasks should reflect all the information contained in the original claim. And also, they should be correctly integrated to reach the final answer. We call this process the logical process. Meanwhile, in this pipeline, we also should ensure that the reasoning process need to use retrieved evidence for subtask reasoning, leading to correct and exact answer. We call this process the causal process. But existing methods often struggle with some issues, including logical flaws and causal errors. The logical flaws is due to exist in the subtask decomposition and integration. The causal errors exist due to the insufficient evidence or hallucination in LLM. Existing methods also suffer from low interpretability. In this work, we propose a multi-agent system for fact-checking, where agents can make decisions autonomously and Our system allows interactions among agents and with external environments. To address the issues existing in the previous methods, we present a logical evaluation agent, which deals with the logical flaws, and also counterfactual evaluations agent, which deals with the causal errors. Our method also provides a structured and a detailed solution, which improves the interpretability. Now I will detail our method for fact-checking. This is an overall view of our method. Our method begins with the decomposing agent, which decomposes the input claim into simpler subtasks. Then we retrieve evidence for the subtasks. Then conduct subtask reasoning followed by evaluation, including logical evaluation and causal evaluation. Next, we come to confidence updating. In this stage, we update the confidence level of each label according to the evaluation results. In this stage, our system decides whether to accept the predicted label or conduct the iteration. This iteration terminates until we reach agreement on the label or we reach the iteration limit. Our method has 3 innovative points. First, this is a multi-agent system which cooperates with each other to reach the final fake news prediction. Second, we propose logical and causal evaluation agents, which ensures the consistency in both logical and causality during fact-checking. Our method also provides structured solution and a detailed evaluation process, which enhances the interpretability. First, we introduce the decomposing agent. Look at this example. This is the original claim. Our decomposing agent is responsible for decomposing the claim into several subtasks. The subtasks include atomic claim and single hop questions. And our decomposing agent also generates a reasoning function, which is used to integrate the subtask's results to reach the final label. Then after decomposition, we use a retrieval tool to retrieve necessary evidence for the subtask reasoning. Then we conduct subtask reasoning. Note that we use 2 kinds of reasoning agents, include fact validating agent and question answering agent, which is respectively responsible for validating atomic claim and a single hop question answering. These agents process the subtasks independently, and their outputs are combined with the reasoning function, which is generated in the decomposing agent. Most existing methods stop at the reasoning step, but our local continues to an evaluation stage to verify the reliability of the result. First, we generate the structured solution, which includes the subtasks with their answers. Then we conduct logical evaluation. We check whether the solution logically equals to the original claim by taking the solution as input and generate a new label and check whether the new label is equal to the original label. Last, we conduct a counterfactual evaluation. In this evaluation step, we determine whether there is a contradiction between the solution and between the solution with the predicted label and the counterfactual label. Namely, we challenge the original label by assuming the opposite label and take it as input of LLM and see whether there is a contradiction. After evaluation, we enter the confidence updates stage. There are 3 cases. If both evaluation agents accept the label, we will accept the label. If only one evaluation agent accepts, then we will increase the counter for the current prediction label and start a new iteration. If both agents do not accept the label, then we will increase the counter for the opposite label, namely the counterfactual label, and then start a new iteration. The final label is determined either when both evaluators agree or when the maximum number of iterations is reached. Now we show our experiments. We conduct experiments on both settings, including the gold evidence setting and the open setting. Our datasets include hover, 2-hop, 3-hop, and 4-hop claims, and feverish. Our baselines include pre-trained models, fine-tuned LLM, fine-tuned models, large language models, and multi-agent systems. For fair comparison with the existing multi-agent systems, we use the same setting for decomposing agent and evaluation agent, including reasoning agent. The setting is followed. It follows the previous works for fair comparison. This is the results of our experiments. As we can see from this table, our method outperforms all the best baselines in both gold and open settings. And we can also see that generally multi-agent systems clearly are superior to single LLM methods. And in open setting, our method has a bigger improvement compared to the gold setting, since open setting is more difficult, and thus our method shows better advantages. Under the gold setting, our local is better suited for the challenging datasets like hover, 4 hops. We also conduct ablation study. As we can see, without our evaluation agents, on average, the results will decrease by more than 1 point. And we can also see that our causal evaluation is more important than the logical evaluation. We also show the percentage of 4 corrected error types by our method. This is a case study. As we can see, this is the original claim, and it is false. But in the original prediction, we predict it as true. After our logical and causal evaluation, we can reach the correct result, namely it is false. We also conduct our experiments in closed setting where there's no evidence. And the result also shows the advantages of our method. Now we draw the conclusion. In this work, we first propose an LLM-based multi-agent system considering both logical and causal consistency for fact-checking, which provides structured solution and detailed evaluating process to improve interpretability. Second, we innovatively apply logical and causal evaluating agents in fact-checking, which examine whether the solutions are logically equivalent to the original claims and assess whether the solutions still hold when challenged by the counterfactual labels. Extensive experiments demonstrate local significantly outperform state-of-the-art methods across different settings. In future work, we would like to extend our model to more real-world cases like fake news detection and multimodal fact-checking. Thank you very much.
Thanks for the talk. My question is, how should the threshold of the maximum iteration number be set? And is the model robust to this hyperparameter? Thank you.
Okay, thank you for your question. In our experiments, we set the maximum iteration number as 2 or 3, because in our experiments, we find that about 2 or 3 rounds, we will achieve the final answer. Yeah, we can reach the correct answer.
Okay, thank you.
Thank you.
Thank you for the talk. My question is, I'm not sure if you mentioned in the talk, but my question is, can you share some details about the retrieval, like what search engine do you use and how do you rank the result and extract the like?
Okay, for the evidence retrieval, we use the same method in our compared baseline, namely PACA, yeah, and program FC. We use the same retrieval step, so we did not put emphasis on the retrieval. Yeah, we retrieve top 5 relevant evidence pairs. Yeah, thank you.
Thank you very much.
Hi, thanks for the presentation. I'm also studying fact-checking. I have several questions. So the first one is the local fact-checking framework involved in multiple agents and multiple steps. I was wondering, for every claim, I mean the simple claim, is also have to go through all the module, like decompose to subquery and literally verify each query. Does it have to do that?
Okay, you mean in the iteration, we need to decompose the claim. I think, yeah, maybe, yeah, in our loop, the decomposing agent is included in the loop. So if this starts a new iteration, it will re-decompose the claim.
How about for very simple claim, like, for example, the web conference hold on steadily, is that sure or not? For this simple claim, does it have to go through all the steps in the local? Like, I will decompose this claim into several steps.
This is automatically generated by the LLM agent. We did not redefine the number of subtasks. Yeah.
I think it also introduced the additional cost for the simple fact checking. I mean, just my suggestion, if you can put additional performance metrics like number of code in your experiment results, which we can show how efficiency of the framework. Yeah, thank you.
Yes, okay, thank you. Thank you for your suggestion.
Maybe let's do one last question, and then if anyone has any questions, we can ask the speaker.
Thank you for the presentation. I observed that even if you don't have the eval and the C stuff, even without the ablation stuff, even then you're sort of outperforming the generalist best benchmarks. So I was wondering, why do you think your particular architecture is outperforming the best baselines, and do you think the difference will still exist if the underlying models are improving? So if instead you ran this experiment with like thinking models and the latest LLMs underneath existing generalist multi-agent frameworks, do you think your architecture will still outperform the existing benchmarks? And why do you think, what is fundamentally different about your architecture that makes it better?
Okay, firstly, because although existing work also use multi-agent systems, but they usually stops at the subtask reasoning and integration the subtask results. In our multi-agent system, we add evaluation stage. Because of the added evaluation stage, we need to consider the overall interaction between these agents. So there's a difference between existing multi-agent agents. The most innovative point is that we propose the logical and causal evaluation. This is very innovative point to explore in fact checking. And we also show the effectiveness of this logical and causal evaluation. Although you see this improvement is relatively slight, but you can see in the hard question like hover for hop, the improvement is very three hop or four hop. The improvement is relatively large for difficult claims.
Thank you.
Thank you.
So with that, that should be the last talk for this session on responsible web. Let's thank all the speakers.